Hello, everybody, and welcome back to my basement. I'm here to record today example 7 from PSQF 6242, in which we're going to examine the same model coded 3 different ways. So the key feature that makes this example different from previous examples is that it features an interaction between 2 categorical predictors. So one is sex, which is coded in a binary fashion, and the other is dementia group, which is a 3 category variable. So in this example, I'm first going to show you how one would examine the interaction between these 2 variables in which each variable is represented via a series of manual contrasts, so you doing the dummy codes yourself. Then we'll show what it looks like if we dummy code just sex and let the program do the dummy codes for dementia. And then we'll see in a third model the same exact results asked for differently because the program has coded each predictor as categorical internally. So away we go. Just to remind you that these are the data that were featured in example 5b and example 6. They're from my textbook, chapter 2, in which I am predicting cognition, which is a measure of crystallized intelligence, what's known as the information test. It's a test that is not supposed to indicate declines unless we have some sort of serious problem, so we wouldn't expect normative age changes here. We have a variable as a predictor of age, which is centered at 85 years, given that this example features older adults. It's fake data, but they're based on real data with older adults. A measure of grip strength is a predictor, which is a proxy for physical function. It's measured in pounds per square inch, centered at 9. As I said, we have a binary predictor with men as the reference group when we're doing our own coding, and subsequent dementia status, which has 3 levels. Never going to have it is the most prominent as coded 1, eventually going to have it as a 2, and currently has it as a 3. So given that this is a 3 category variable, we're going to have 2 contrasts to represent the differences between the 3 groups. And those 2 contrasts will be able to recreate all possible means for each group as well as all possible group differences. The previous model in example 6 also had an interaction term of age and grip strength. We examined that as the last model in example 6. So if you want to get an example for how to examine interactions between quantitative predictors, each of which is linear, that example will satisfy that. For now, we're going to turn to what the model would look like with an interaction between sex and dementia group. So the data preparation here in SAS as usual. This is an example of how one would import a SAS dataset directly into SAS. So the file save abbreviation that we have used previously to represent a shortcut to the file path for any type of file is now being invoked to create what is known as a SAS library. So this ampersand file save means put this wherever you see that. So this file save is an abbreviation. Given that it's referring to the same place, I have also named my permanent SAS directory file save. So down here on the data statement, what's happening is that it is going to read in the SAS Chapter 2 dataset with no extension. Since it's a SAS dataset, it understands what the extension should be. That is saved in this file save location, which we have defined up here. It's going to read in the data and save a copy in the work library, which is a temporary directory, and it's going to be called example 7. I always recommend doing this, reading in an original SAS dataset in a permanent directory, making a copy into the work library. That way, if you do any data transformations that mess something up, the original version of the dataset is safe and sound over here. Given that we're going to be working with categorical predictors, I have also used a proc format. This is the analog of variable value labels in SPSS, or I think it's value labels in Stata as well. And so these are labeling conventions that I am defining. So I put an F in front of my labeling convention names. That stands for format in my head. So FDEM group is a labeling convention that's going to be applied to the dementia group variable. fsex is a labeling convention that is going to be applied to the gender variable. The actual application of these value labels happens down here in the data set. So I am going to tell it, for these particular variables in this data set, use these labeling conventions. And you'll note that inside each label, it starts with the number that corresponds to how it is actually represented in the data set. I do that because otherwise SAS lists these in alphabetical order rather than numeric order, and I want them to stay in the same order in which they were originally coded for my own sanity. So in terms of preparing the rest of the data, I'm centering my quantitative predictors. My convention is always to create a new variable that has the centering constant as part of the name. That way I don't have to remember what it is when I'm looking at my output. So this is new variable equals old variable, and it's minus 85 here because that was near the middle of the distribution for age. Likewise, 9 was near the middle of the distribution for grip strength, which is pounds per square inch. To create dummy-coded variables to represent the differences between the three dementia groups. Here's the usual process. I'm beginning with code to create two empty columns. So I am creating two columns and setting them to be missing. That's what the dot means. My column names are dem NF, which is going to stand for none versus future, and dem NC, which is none versus current. Technically, I don't need to do this step. It's sort of implied by what comes next, but I'm doing this to keep the syntax as parallel as possible to what happens in Stata for pedagogical purposes. I am then going to fill in a pattern of zeros and ones that corresponds to how I want these variables to be interpreted as a function of the original variable for dem group. So the one group is none. For them, I want them to become the model reference, and so both of these contrasts are coded 0. For the group coded 2, I want the first variable to distinguish group 2 from group 1, therefore I'm putting a 1 here. And for the third level of this variable, I want the second variable I'm creating to distinguish group 3 from group 1, and so a 1 goes here. So this coding scheme then creates the interpretation of none versus future for the first variable and none versus current for the second. Sex is already coded so that 0 stands for men in this example and 1 stands for women. So I have that just reiterated in the labels here. And then applying the format. So the format statement is used to apply all different kinds of formats in SAS. In this particular case, we are saying, hey, take my gender variable and apply this labeling convention defined up here. Take my dem group variable and apply this labeling convention defined up here. That's because in some of the models, we're going to use the original dem group in the analysis and let SAS do the internal dummy coding. That way we have labels that will help us refer to what they mean. And then last but not least, whether you like it or not, any case that is not complete on the variables in the model is going to be excluded from the analysis. So I usually try to address this ahead of time in order to keep the sample consistent across my models by deleting cases with missing values. If you'd like to learn about alternatives that would be a better choice than dumping cases, please come to my advanced classes that use likelihood estimation instead of least squares. Here are the same steps in Stata. So defining a file save abbreviation and then invoking it here. I am importing a Stata dataset directly into Stata, and so I can do that with the use option. Note that the name of the file that I'm going to be importing still includes the extension. And clear just means that if it's already open, just go ahead and write over it and re-import. So this is good if you need to go back to a fresh data set if you screw something up. That clear option allows you to do so. One thing that I note is that in building this original data set for my Chapter 2 examples, I had created it by exporting it from SAS into Stata. That process automatically converts all variable names to lowercase. That's not an option that you can change as far as I've been able to find. If anyone out there knows better, please let me know how to do that. So all of the names have to be consistent with the case in which the variables have been stored. So that's why, for instance, my NF is going to be lowercase. Everything is lowercase in Stata. So I'm switching to lowercase because case sensitive matters in Stata. And I cannot use my preferred title case version of naming variables. So gen is used to create new variables. It's the new one equals the old minus whatever constant you're trying to center at. I am then using a combination of gen and replace to do my dummy coding. So creating my two new variables here, setting them to missing values, and then systematically replacing them into the same patterns of zeros and ones as discussed earlier to denote the none versus future as comparing group 2 to group 1, and none versus current as comparing group 3 to group 1 instead. I am creating value labels and implementing them within the dataset within this step right here. So label define is the analog to proc format. You can create a labeling convention, and I have done so and called it fdem group. I am then applying the labeling convention under the label values. So just like in SAS, the convention is stored separately. That way you can apply it to more than one variable at a time. And the same thing is happening here in labeling gender. Now we have labels for all the other variables, and then last but not least, I'm kicking out any cases that would be missing on the variables that will be included in the model via thisegen, which I think of as fancy gen. It is using a function called rowmiss, which is the analog to nmiss in SAS. It's creating a new variable that holds the number missing and then dropping cases if the new variable is greater than 0. Before diving into the results, I have a paragraph here denouncing ANOVA dogma. So in the context of these models in which we're including categorical predictors with more than 2 groups, I guarantee at some point someone will start yelling at you about type 1 error control or family-wise error rate when you go and look at different pairwise contrasts between each of these groups. They are not wrong. If you use an alpha of 0.05, then 1 in 20 tests would be significant even if the null hypothesis is true. That's what alpha means. That's your acceptable type 1 error rate. The problem that I have is that that is somehow remembered in a much more pronounced way when you're dealing with categorical predictors than if you're dealing with other terms. So for instance, if I look at this model, I've got 2 effects here, I've got another effect here, but it's only those that pertain to gender or dementia group that people would worry about needing to control for type 1 error. The way that it is treated in regression with quantitative predictors is inconsistent with the way that it is treated for categorical predictors. So I'm not going to show you or worry about extra levels of type 1 error control for this example because it uses categorical predictors than I would normally worry about for any example. If you know that you have a lot of groups, or if you know that you're going to be doing a lot of tests, pick a lower alpha rate. It doesn't really matter what your model is. The same principles in terms of type 1 error control should hold regardless of what you're doing, but they don't in practice. So I'm not going to worry about it. I'm going to leave that to someone else. As a point of reference, here's the data. So when I initially learned analysis of variance, so what we're going to be doing here is functionally known as a two-way analysis of variance, or ANOVA. I learned it by staring at tables like this. So terminology here, what I have is a cross tabulation of the dementia 3 groups, none, future, current, and the 2 groups for gender, men versus women. And the values inside this table are what's known as adjusted means. I'll show you where they came from in just a second, but they are the group means holding age at 85 and holding grip at 9. So inside the table, the unique combination of each level of the interacting variables is what's known as a cell. And out here, the average across cells of a table is known as a margin. So the overall mean for the none group, say, is known as its marginal mean. Here's the overall mean for the future group. And the way that these means are computed is by averaging across the groups equally weighted. So this is potentially problematic if you have cells that are really uneven, but that is conventionally what happens. You treat them as if they're balanced and creating these marginal means. So I want you to be aware of the terminology that I'm going to be using. What I care about is right here, because an interaction term between men and dementia group can be interpreted as saying that the effect of dementia varies by gender, or the effect of gender varies by dementia. And these 6 means and differences between them, and differences of those differences, are what's going to tell us the story of the interaction. These marginal things out here don't really tell us anything because they average over the levels of the interacting variable. Unfortunately, you will see that when these variables are treated as categorical by the program, the marginal means are what are being tested, and you have to dive deeper into the software beyond the defaults to actually get the interaction contrasts of interest. But no matter how we slice it, this is the data that we're going to be analyzing. And for this particular example, we're focusing on just this interaction term between men and between dementia, which is going to require 2 degrees of freedom given that dementia group has 3 levels. So the linear model that corresponds to what we're doing is right here. So we're treating cognition as a quantitative variable. We have what are going to be simple main effects of age and grip strength, because we also have an age by grip strength interaction. Again, example 6, the last model was focused on that. We have a simple main effect of gender, and I say simple main effect because it interacts with dementia group, and likewise we have simple main effects of dementia group because it interacts with gender. So that's the model. Regardless of how I specify it in the software, this is what the model is going to hold. So the first option is to do the coding for sex and dementia group myself. This is the way that I have been teaching all semester because it most directly corresponds to this linear model representation, and it makes sure that the user understands what all they are asking for in fitting an interaction term that requires more than 1 degree of freedom. So I have organized my line of fixed effects here so that all the terms that relate to each other are next to each other. So we're starting with the age, grip, and their interaction term. Remember, in SAS, you can define an interaction term with a star without having to create an observed variable in the dataset. Here are the simple main effects of gender and dementia group, and then here are the 2 new interaction terms that we're going to be adding to the model. So we want to know if, as a set, these 2 new terms significantly increase the model R-square if they account for significant variance as a set. And as a set is important here because it takes 2 fixed effects conceptually to represent the full pattern of the interaction between sex and dementia group. So just like we did in previous examples, anytime that you add more than 1 fixed effect to the model, you would need to ask for an F-test that lumps together those new fixed effects to test their joint contribution to the change in the R-square. So I'm doing so in SAS using a contrast statement, and I note the comma between these 2 terms. So I need 1 of each interaction term to go into here, and the comma separates out the numerator degrees of freedom. So SAS understands I am asking for a joint test of 2 things because of the comma. Now that is important to emphasize because of the contrasts that follow. This is something that you have not seen before, and to be truthful, it's something that I just recently figured out how to do in order to make this example parallel across all 3 different ways of representing the model. Pause for a coffee break. There we go. So I am demonstrating how to create a simple effect of dementia that is conditional on the interacting variable, but that lumps together all of the fixed slopes that go into creating that simple effect. So because there are 3 group differences for dementia, I can ask for the joint test of the 2 slopes that create those 3 group differences in men, as well as a joint test of the 2 slopes that create those 3 group differences in women. That's what I'm trying to do. So the first contrast here lumps together the main effect of dementia with the interaction term with sex so that I know for whom this is the main effect of dementia. So this combination of what it is in men plus zeroing it out for what the difference in women creates the effect for men specifically between none and future. Then I have the comma that distinguishes a second effect, which is the difference between none and future, also in men because the interaction term is a 0. So contrast this pattern with the pattern that is immediately below it, which is how I get the simple effect of dementia for each slope for women. So it's what it is in men plus the difference for what it is in women. So those 2 terms, when added together as a linear combination, create the none versus future difference in women. So that's one of the components of my contrast. The none versus current difference in women is the other component of my contrast. So even though there's 4 terms here, I'm actually just testing 2 slopes because the terms that do not have a comma are literally added together. So I have 1 degree of freedom here and another degree of freedom here. So on the whole, testing whether this group difference is significant in men and whether it's significant in women. Then we'll dive in more specifically to get the pairwise differences among the 3 groups. I am saving the next line of code here, some of my results. So I am asking it to create a new data set that is called Pred Outcomes in the work library because I am asking it to build predicted outcomes for all the cases in my data set. The predicted outcome itself is going to be stored in a column I am asking it to name as y hat, and the standard error of that prediction I am saving in a column called SE y hat for standard error. Here are the adjusted cell means. And so note, because age and grip are not part of these lists, that means I am holding them at their 0 values, which is here given my centering when age is 85 and grip strength is 9. So when I'm creating these adjusted cell means, these are y hats. So I can call them group means because that's what I'm talking about, but they're y hats for certain kinds of people. So they need an intercept, and we need to know whether each of my gender and dementia variables needs to be 0 or 1. So if it's men with the none group, that zeroes everything out. For instance, if it's women in the current group, then everything has a 1, or this has a 1, this has a 1. And then the interaction terms multiply the patterns given here. So then this is a 0 because this is a 0, and this is a 1 because this is a 1, and gender is a 1. We can then look at simple effects of sex per dementia group and simple effects of dementia per sex. So going back up to the table, now I want to dive in to the cell means. So one set of comparisons I might be interested in is the difference between men and women conditioning on a moderator of dementia. So that difference, and that difference are given by these 3 estimate statements. So the logic of these estimate statements when you're generating predictions for the simple slope for particular values of your moderating predictor, the formula is always the same. You need all of the terms in the equation that have the simple slope of interest and none otherwise. So for instance, I want the gender slope, so I need a 1 here at a minimum. The simple main effects of dementia group are irrelevant because they don't have gender in them. Then I need to know for what kind of person do I want the gender slope for. And in this case, the none group is when both of these dementia contrasts would be coded 0. The future group is when this one's 1, and the current group is when this one's 1 instead. So it's going to be a linear combination of whatever the main effect of gender is in the none group, plus how it differs in the alternative group, gets us to what it is going to be in the alternative group. So those three are going to give us this difference, this difference, this difference. Then we can go the other way. So previously we asked for a 2 degree of freedom F-test to distinguish those three means. Now we can dive in more specifically to get the pairwise differences. So within men, what is none versus future, what is none versus current, and what is future versus current. So I have each of the dementia group differences within each of the two genders, and the same logic applies because now I'm focusing on the dementia group differences and none future difference specifically. I need all the terms in my estimate statement that contain that DEM-NF code that I'm interested in and none others. So because I want the dementia group difference, the main effect of sex doesn't have it, it's zeroed out. I want this difference specifically between none and future, so none versus current is zeroed out. And then the moderator turns on or off as a function of which type of gender I want the dementia group difference for. I want to draw your attention to the last line here. This one has some minus signs in it. That's because this is referring to the dementia group difference that is not directly provided by the model and instead is implied by the model as a linear combination of the differences in the slopes. So for instance, if I go to this line right here, future current in men, where that comes from is this line minus this line. Let's see if it will let me do 2. There we go. So the third one minus the first is what is going to create the fifth one. So all the gender effects are zeroed out. We have 0 right here on the third, minus 1, that gives me my minus 1. We have 1 minus 0, that gives me my 1, and the other terms are zeroed out. And this one right here for women, that is the result of line 4 right here minus line 2. So in this case, gender differences are zeroed out. We have 0 minus 1 gives me the minus 1 here. 1 minus 0 gives me the 1 here. And we have 0 minus 1 here gives me the minus 1. And 1 minus 0 gives me the 1. More generally, the pattern can be understood as the slopes that correspond to the first term that you want to use as the reference for the contrast get a minus 1, and the slopes that correspond to the alternative group for which you want the distinction to be made get the 1. Now we have all of our simple effects to be created, but we don't have the interaction term yet. So to go up to the table here, our interaction term tells us how one of the group differences differs as a function of the other. So in other words, let's say this gender difference right here, that's approximately 3 points, a little under. Is that gender difference different than this gender difference, which it looks to be much bigger? Numerically, sure, these numbers look different. The difference of 3-ish is different than the difference of 11-ish. But are they significantly different? That's what the interaction contrasts have to tell us. Is this gender difference different than that gender difference? Interaction contrast. Is this one different than this one? Interaction contrast. We can also look at it the other way. Don't mess with my table. Is this difference between the none and future group in men of about 6 points different than this dementia difference in women, also about 6 points? Doesn't look like it in this case. But what about this one? This difference of about 12 points versus this difference of about 20. So this is what I mean by the difference of the differences. It's the difference in the table going one way. Does that difference vary if you go the same way across the table in a different row or in a different column? Fortunately, the simple group differences here, the pairwise differences, give us all the ingredients that we would need to know to get those differences of differences interaction contrasts. So for instance, if I want to know if the sex difference differs between none and future. So if I want to know if this difference differs from that difference, then I need to know what the gender difference was in none as the reference point and compare it to what the gender difference was in future. So if I take the second line and subtract the first, the main effects of sex drop, the main effects of gender were all zeroed out anyway. I have 1 minus 0 and 0 minus 0. So the only term that's relevant is right here. And that's because that interaction is directly the answer to the question as to whether the gender difference differs between none and future. Likewise, if I want to know about the gender difference between none and current, that's directly given by the second interaction. And if I want to compare the future and current, that is this one minus that one. So the minus 1 goes to the reference of the contrast, and the 1 goes to the alternative group. And I have written these out two different ways to make the point that you can interpret an interaction between two variables from either perspective with respect to which is the moderator. So I could talk about how the sex difference differs as a function of dementia. I could also talk about how the dementia effect differs by sex. So we're talking about this difference differing from that difference. Another way of saying the exact same question is this difference differing from that difference. Because I can get to this same result with only this term being involved if I start from, let me find them, the none-future effect differs by sex, these two lines. If I take the second line and subtract the first, I end up at the same place. And the same is true for all of the other possibilities. So even though this model only includes two different interaction terms, it's actually generating three different single degree of freedom contrasts in terms of what the pattern of the interaction could be. And so it's useful to ask for all of them to really understand what the pattern of differences is. Whew, that's a lot of code. I'm going to pause, reload my coffee. Then we get to do the same thing in Stata. So Stata uses a hashtag or a pound sign if you're old like me. Note that in earlier versions of Stata, I think they've changed this in 16, but if you want your code to be backwards compatible, you need a line continuer. Anytime that your stuff that you're including in the same command takes up more than one physical line of code. Test statement is the analog to contrast, so these are the lumping together of predictors to generate f-tests. Unfortunately, they do not get effect sizes like they do in SAS, but you do get the f-tests. So this first one, for instance, is testing the addition to the previous model, the two new interaction terms, and asking whether or not they significantly increase the R-square. And the second set of test statements here, these are the simple main effects of dementia within gender but lumping together the two contrasts that are needed to create the total omnibus effect of dementia. So just like up above here, where we had this pattern where that's one term and that's the second, these are still 2 degree of freedom tests. I'm doing that within a parenthesis. So parentheses denote degrees of freedom for the numerator of the test. So that's one thing. So we're literally adding together this pattern to create one simple effect of what the dementia group would be for men. Here's the other simple effect of dementia for men, and those things together would create the missing third difference. And for women, then we have this lumped together and this lumped together. Next, we have adjusted cell means. So these are holding age and grip constant at their centering points, 85 and 9. It's asking for the range of means varying gender for each of the possible groups. So the way to interpret these parentheses, the first number is where it starts, the second number is the increment it increases by, and the third number is where it ends. So this is start at 0 in increments of 1 and go up to 1. So that's going to give me 2 means for the 0 group and the 1 group for this combination of holding everything else at 0. So the first line gives me 2 means, 2 means, 2 means. Then we have LINCOMs that are creating sex differences conditional on dementia as the moderator. So the format of these is the same. Because we want the sex difference, that gets a 1. And then we need to know for which group we want the sex difference. The none group is where both dementia contrasts are zeroed out. The future group is where the first one is 1, and the current group is where the second one is 1. Then we get into simple effects of dementia per sex. And so then we need the simple effect for whichever contrast we're talking about, so none versus future in this case. And then we need for whom are we talking about it. And these will only take a value of 1 if we're talking about women as the alternative group. And then we see the same pattern of model-implied dementia group differences that are linear combinations of the dementia contrast we created, where -1 is applied to the reference group for the comparison, and 1 is applied to the alternative group for the comparison. And the interaction terms then control whether or not it's for men, which is zeroed out, or whether it's for women, in which case the pattern of -1 and 1 is repeated because it's implicitly multiplied by 1. And these simple effects then provide the necessary ingredients for creating interaction contrasts in the same pattern that give us the differences in differences. So whether or not the effect of gender varies between none and future, or whether the none and future difference varies by gender, for instance, those are 2 different ways of saying the same thing. And then we have the other 2 sets of possible combinations. Okay, man, time flies when we're building interaction terms. Good stuff, huh? I apologize, by the way, that the video is not more interactive or interesting, but hey, you get what you pay for. So here's our results. This output is going to be the same for all 3 models that we look at. So what this is telling us is whether or not the 8 slopes that are part of our model work together to significantly predict cognition. The F-test says yes, they do. This is the per slope sort of average contribution, and the 8 slopes are doing a good job working together. They capture about 30% of the overall variance in cognition. Then we get a more fine-grained assessment of what's going on in the model. This table right here, I normally omit because its information is redundant in terms of the F value with what is provided by the solution for the fixed effects. But I'm including it here to show how it's going to change as a function of how we specify this same model. So at this point, SAS does not understand that these are somehow lumped together and that these are somehow lumped together. And so each of these is the simple effect for the variable that it interacts with being 0, and that provides the corresponding effect sizes in semi-partial eta square down here. So semi-partial eta square is the amount of variance that is uniquely attributable to that fixed effect. So I have a note out here, this is Proclisa trying to help you out here, as to whether or not these things should be reported or reported conditionally. And just to remind you, because age and grip strength interact, this age simple effect is specific to when grip strength is 9, and this grip strength simple effect is specific to when age is 85. So these effect sizes are also conditional. I think it's okay to report them so long as you do so correctly and indicate that they are conditional, and that if you chose to center these predictors at a different place, these numbers would adjust accordingly. The interaction term between them, though, is unconditional, and that can be reported as is. Same thing with the main effect of gender here. It's conditional on the none group, given our centering choices. That's where these things are 0. In contrast, none of these is really okay to report by itself. That's because SAS needs to lump them together to represent the commonality of these contrasts. These two share a common reference group, as do these two. So I did the lumping myself by creating these contrasts from before. And so I have added the output from that separate table to this one to save some space. But this, for instance, is the lumping together of these two terms. So this covers the overall degrees of freedom to interaction. This one is the simple main effect of dementia across the two contrasts for men, and this is it for women. So these would be more specific ways to carve up this pattern of effects. Then we get into the F-tests that go with these effect sizes, and it looks like they're all significant. So adding the two interaction terms to the model did improve the R-square relative to the previous model, so it would make sense to keep them and interpret them. Here is the table of fixed effects, and so I have tried to help you link these back to the equation, and then we can go through this listing of fixed effects. So the intercept, always the expected outcome when your predictors are 0. So in this context, given the way we've defined the predictors, 29 is the expected cognition score for an 85-year-old with 9 pounds of grip strength. Not any changes based on the interaction term. For a man who does not have dementia, no changes based on the interaction term. So whenever you're adding interactions of predictors that are already part of the model, you're not changing for whom the intercept is the reference. The value covered by the intercept may change though because the model predictions have changed, but who this pertains to is the same. These parts of the story are very similar to what they were in the previous model. It looks like we have a simple main effect of age for grip strength equals 9. That's negative. That simple main effect becomes less negative as grip increases. So less negative by 0.12 per pound of grip strength. Likewise, the simple main effect of grip for an 85-year-old is significantly positive. It becomes more positive by 0.12 per year of age. And in example 6, this was the last model. We went into this interaction term in more detail and looked at regions of significance and all that kind of fun stuff. For today, we're focusing on this part of the story. So each of these effects is conditional on the interacting variables being 0. That means that this is the gender difference. Given the way that it's coded, men is the 0, women is the 1. That means that women are lower. That's what the negative slope means. The one group is lower by 2.88, but that is specifically in people who do not have dementia. Do I have the table? Yep. So that is that difference right there. That's what that is telling us, because none is where dementia group is coded 0. We can hold that as our reference and think about dementia group as a moderator, and then first look at this interaction term. So what this is telling us is that as dementia goes from 0 to 1, So this variable represents the difference of how none compares, or future compares to none. So as we go to the future group, that gender difference favoring men becomes smaller. This is a less negative by 0.16. So there is a slightly smaller gender difference in the future group. It's smaller by 0.16. So that is giving us how this gender difference compares to that gender difference. The difference is only 0.16. If we start here again, gender difference in the none group, now we can talk about how it compares to the current group, that one. So as this dementia moderator goes from 0 to 1, that means we're going from none to current. So the gender difference in the current group of minus 2.87 becomes more negative. So this is a stronger moderation. The gender difference grows, becomes more negative by minus 7. So if you put those together, the gender difference in the current group is around minus 9. So that is shown to us down here as how this difference differs from that difference, which is, I guess it's only 8. So my rounding is off, but that's why, no, wait, it's only 8. There it is. That's why we ask for SAS to do the math, because Lisa is bad at math in her head, especially while she's trying to walk through SAS code and interaction terms. The other way that we can talk about these interaction terms is by starting with dementia group as the focal predictor and using gender as the moderator. So each of these dementia group differences of how the future group compares to none, how the current group compares to none, those are both for men. So to talk about what they are in women, then as the sex moderator goes from 0 to 1, then we go from 0 men to 1 women. This difference of minus 6 becomes less negative. That's a positive coefficient, so it's smaller by 0.16 in the women group. So then if we go down to our handy dandy table, now you're seeing why the tables are very helpful to look at. We are talking about that difference differing from that difference by only 0.16. Then we have this one, which is how current differs from none. Current is lower by about 12. And in women, they're more lower, so this is a more negative, stronger effect. The gender difference is bigger by 7. So in the current, nope, in the women's group, the non-current difference is like 18 or something. Let's see, yeah, there it is. So what is not evident from this table, but what this table does still allow us to predict, are the differences between the future and current. So the differences between these two slopes of about 5, that's the future current difference in men. And so then the difference between these two slopes then tells us how that future current difference differs in women. And I'm not even going to try to do that math in my head. Instead, I'm just going to swing down here, and we have this difference, so which is about minus 6 in men, corresponding to a difference in women of about minus 14. And that is the model implied interaction here of minus 8. So it's the difference of these two numbers right here. So that's the one that the model predicts, but the model doesn't give us directly. We have to use a linear combination of the difference in slopes to get there. So now we have the full story summarized out here for our ease of reference. There is an advantage for men in the none group. There is an advantage for men in the future group, but it's not significant. And that boils down to sample size. There's a lot fewer people in these two groups. And there is also an advantage for men in the current group, which is significant. If we want to compare the sex differences across, then the non-future gender difference, so that difference and that difference are not different. This difference and this difference are different, and this difference and that difference are different too. And I'm pulling those numbers from down here to make those conclusions. So a somewhat complicated picture, but now we have all of the information and p-values that would be needed to flesh out that story and fully talk about how each of these effects varies as a function of the other. And as we discussed in class, never, ever, ever put this into a presentation. Instead, give them a picture. So I save the results of my predicted outcomes. I'm plotting prototypical outcomes for all possible combinations. So some people would say I need a bar graph instead of a line graph, but whatever. You can quibble with me about my choices, but the pattern is what I wanted to show. So on the x-axis is dementia group, and women are the red line and men are the blue line. And so what we can see is that the difference between these groups, men and women, is widest for current. Having dementia is bad for you, particularly current dementia relative to the other two. It's more bad if you're a woman. So the plot really makes the pattern of the interaction jump out. For completeness, I would probably add some error bars to these things, and that information is available in your data set if you use the standard errors that come from the model. That way you can convey the idea that even though these differences look the same, this one is not significant because the error around it is much larger given the smaller sample size. Here is the same idea, but plotted from the opposite perspective. Now we have different lines for different dementia groups, and the slope of the line conveys the gender difference. And so the green line slope is the greatest. The difference between men and women is the greatest in the current group. All right, so that's what all of this would look like if you do all of the coding yourself to describe the differences between groups as well as the interactions between those differences. So adding all of this stuff yourself. This is a lot of code, I'm not going to lie to you, and there is a way to shortcut this code by letting the program internally do some of this coding. It also simultaneously, though, offers a greater opportunity in my mind for confusion, which is why I wanted to show you this sort of the longhand way before getting into the shortcut way. So that's where the next video will start. What if we let the program do at least some of our coding? So I hope to, I wouldn't say see you there, but I hope you tune in for the next installment of Example 7. Thank you.